Welcome to a sneak peek of Weaviate Standalone. Now I imagine you're in one of two groups. Either you're wondering what is Weaviate, or maybe you've already used Weaviate or have seen some previous demos, and then you're probably wondering what is Weaviate Standalone. Either way, I'm going to define what Weaviate is, maybe even redefine it depending on how long you've been with us, because some things have definitely changed in Weaviate. And then I'm going to get into Standalone, which in my opinion is the most exciting thing to happen to Weaviate so far. So what is Weaviate? If you're new to Weaviate, Weaviate is an open source cloud-native real-time vector search engine with a graph-like data model. Now I've mentioned three parts that I think we should talk about further. First of all, cloud-native. There's going to be a later video where we talk more in depth about how to run Weaviate in a distributed setting and how to horizontally scale it. So for now, just know that Weaviate has always been built with the intention of running it in the cloud, in a production setting, in a Kubernetes cluster, for example. So what we have left is a vector search engine and a graph-like data model. And I'll get into those two in a bit more detail now. So what's a vector search engine? Vector search sometimes is also called similarity search or neural search to really highlight that AI machine learning character of a vector search engine. So what do you do with it? Imagine you have a big pile of data. I've used 1 terabyte here. It doesn't matter, just a big pile of data. This is probably unstructured. It's maybe from multiple sources. Maybe it's a dump from your ERP system, or maybe it's email communication that's been going around inside your company, or something else. It's a lot of data. There's probably a lot of very good information in there, but it's very, very hard to get it out. So you could be asking yourself questions about your data set. For example, how much money did we spend on traveling post-COVID-19 lockdown? Or maybe you're thinking, where can I find publications that are related to machine learning? And in both cases, you know that the answer to those questions is somewhere in that data. But essentially, you're presented with several problems. The first of all is that this chunk of data is really large. Even if you know how to access that information, you need a system that's efficient in going through there. You can't just, on any query, you can't just iterate through a terabyte of data, unless you're okay with like 10 or 15 second response times to your queries. But as I said before, Weaviate is a real-time vector search aimed at production cases. So while I don't like 10 to 15 seconds, I do like 10 to 15 milliseconds. So the first one is just you need something that's capable of handling large amounts of data at scale in real time efficiently. The second problem is the unstructured nature of your data. So if you think of a SQL database, for example, where you have tables, then you could form a nice SQL query where you say, give me all the entries where category equals travel. And that's nice in theory if you have that kind of structure. But what we see in real life is that you don't. Maybe something in there is an email that doesn't have any structure. Something else is maybe taken out of an SAP system. The third one is an invoice that was scanned and just ran some OCR, text recognition, on top of it. So we really have all these kind of different structures. But that on itself is not yet sort of the vector search problem. You can still use a typical enterprise system where you just index everything and then you can have these sort of free text searches around everything. But now the real problem comes in. What if those invoices and things, if they don't necessarily mention traveling, maybe it says airline ticket or train ticket, or it's just an invoice for gas. So here the first problem is that if you really wanted to do a sort of text-based search on finding everything related to traveling, the first thing that you would need to do is classify what is traveling information in there. And a lot of companies do that manually these days, but with a vector search engine, we want to rely on machine learning models to do that automatically. Similarly with publications related to machine learning. If your publication literally says machine learning in there, it's very easy to find it using something like an inverted index that also works very well with the 1 terabyte scale. But the problem is that it might not literally say machine learning in there. Maybe it could just be something like a synonym. It could be AI, or it could maybe not mention the category at all, but just talk about different technologies or tools. So you'd maybe have something like the word TensorFlow in there. And as a human, you know that the word TensorFlow is related to machine learning, but a string-based search engine doesn't know that. And this is exactly where a vector search engine comes in. So for a vector search engine, we try to vectorize every data object and also your query. So for example, if we have an article that talks about TensorFlow, then this is positioned in a very specific position in a space. And the neighboring concepts around it are machine learning and AI and these kind of different terms. So when a search query comes in, you now essentially turn that query into a vector as well. So a vector is just a long collection of numbers. So it's like 300 or 600 typically, or if you're vectorizing images or videos, it's even longer. But essentially you have this long set of numbers, and now you want to compare it efficiently. And here's the sort of next problem. Even if you have that machine learning model, searching through this in real time is not that easy, especially if you want to have a production quality search engine. Yes, there are libraries that you can spin up and they use a lot of memory, and what if something fails? What if something crashes? What about high availability? All these kind of questions is what separates a simple library from a real sort of production-focused search engine that is Weaviate. So now let's talk about the graph-like data structure. In the simplest term, Weaviate is a search engine, and of course a search engine also allows you to store your data. You store the data in a NoSQL key value fashion. But that's not everything. In Weaviate, you can also connect. You can arbitrarily connect your data points. And this is something that ties in really well with this whole machine learning idea, because data is always connected. So you have this implicit connection based on the vector position that's maybe not obvious through the position. So for example, a graph structure could be something like this. You have a publication. That publication has an author. And this particular author in turn wrote other publications. And then you could say, sort of follow these links to see all the other publications that this author has written. However, something that's very important to note here is that Weaviate is not a graph database. Weaviate is a vector and also scalar search, you'll see that later, first, that optionally has graph features. So if your use case relies more heavily on these graph features, a native graph database might be a better fit. But if your use case relies on the fuzziness and on the search aspect and maybe also classification aspects, then Weaviate is a perfect fit for your use cases. So now that we've defined and maybe even redefined what Weaviate is, let's talk about what Weaviate Standalone is. I said before that I think it's the most exciting change to happen to Weaviate so far. Depending on when you're watching this video, Weaviate Standalone is either a sneak peek of what's to come in the future, or maybe it's already been released. So I'm recording this in September 2020. And at the moment, the development for Standalone is ongoing. And we aim to release it in December 2020. So if you're watching this video after December 2020, Weaviate Standalone might just be Weaviate by then. So what does Standalone mean? In the current generation of Weaviate, Weaviate uses third-party databases in its stack. So if you've run our Docker Compose setup or used our Helm chart to deploy Weaviate in Kubernetes, you might have seen that there are components such as Elasticsearch and etcd. And this has worked really well so far to prove the concept, to prove the additional value that Weaviate provides with small and maybe sometimes even medium-sized use cases. This whole setup was made sort of vector capable, but it was never vector native and it was never vector optimized. And that is exactly where Standalone comes in. So as of now, Standalone is an option. You can sort of use the preview, but it's currently in development, so some features are missing at the moment. But Standalone is the upcoming Weaviate release that no longer relies on any third-party databases. It's a vector-native database and search engine that's built from the ground up around the idea of bringing your machine learning models to scale. So if you compare that to the current release, no features or APIs are removed. So anything that works in Weaviate is going to work in Weaviate Standalone, most likely much better than before. So as I said, the development for this is currently ongoing. So as of now, we don't have this feature parity yet, otherwise it would be released already. We focus on the most important features first, but by the time we release this, you can make this switch very easily because all of the features are still going to be there and they're still going to work. Now, to make a database or a search engine vector native, we've decided to make a vector index part of the core of Weaviate Standalone. With a vector index, you're going to be capable of running very large data sets, so the millions, the billions, the tens of hundreds of billions if you horizontally scale your Weaviate instance or shard your indices. But something that's also important to us, and this is aiming more at the data science community, In Weaviate, we don't want to make this vector index something super opaque or use a proprietary system. So essentially we said we're going to use a technology that's out there, that's proven, that's still new, that's performing well, but also one where you can easily research the advantages and disadvantages for this. The first one that we've picked is HNSW. I'll get into what it does a bit more later, but first let's demo something. But the important thing is, this is just the first one that we support. So we want to have this vector index part pluggable, because we know how different, we know from our own experience how different various use cases are. And sometimes you need a specific model, and sometimes you want to have the advantages of a different model. So in the future, there's going to be this long list of different vector indices that you can use that are very, very tightly integrated into Weaviate. At the moment, HNSW is the first one, and as you'll see in a second, HNSW is responsible for super awesome performance that we have. Okay, so much for the theory. Let's demo something. Okay, demo time. And in order to demo a search engine, you need a cool data set. Now, some time ago, we had an issue on the Weaviate repository from community member Luke Michalski, and he asked if we could present a demo data set that contains the whole arXiv dump. So Luke Michalski is the person behind Paper to Code, a search engine for academic papers, and arXiv.org. It's written like arXiv.org, but I recently learned it's correctly pronounced arXiv.org, is this database of academic papers by Cornell University that are available for free. So inspired by this idea, there's been a very cool collaboration between community member Luke Michalski and our very own Laura. And now we have this demo data set that imports all 1.4 million authors and 1.7 million papers into Weaviate. So I thought that was a perfect example to demo Weaviate Standalone. I have all these papers imported now on a single machine that's running Weaviate Standalone. And now we can send some queries against that machine. In order to do that, I've brought up the Weaviate console that also contains the graphical GraphQL query interface. And here we can send a GraphQL query. So the simplest query that we can send is just a get things. And then here we have our class paper, where we have all the papers imported. And we can just show the title of the paper. And we can limit this to maybe 10 for now. So here you have the first 10 of those 1.7 million papers. No vector search has happened right now. Essentially, we haven't specified anything to search by. So essentially what we've done is just list the first 10 papers. So to make that a bit more interesting, we can specify an explore ranker. I'm calling that a ranker because it's not a filter, because it doesn't remove results, but it just ranks them by how close they are to a specific concept. So in this case, the concept I want to search for, let's say I'm searching for space travel. Cool. What has happened here in real time was a vector search through those 1.7 million papers. And now you can see my search results are all related to space travel. So here I notice the first one, the long-term scientific benefits of a space economy. That seems to be focused on the economy of space. Let's say I'm more interested in the technical side of space travel. For this case, I can move my vector position. Let's say I want to move it away from, and then I can specify another concept. And the concept that I want to move away from in this case is economy. And let's move with a force of, say, 0.8. So if I run that again, you can see that my queries are still focused on space travel, but not so much in the economy anymore. So now the first one is a warm Jupiter and mini Neptune in a triple star system. So because we're not searching by strings, but by vectors, it's easy to move them around in the space, as you could just see. So let's go for a couple of other queries. Let me remove that. And let's say we're going for food and wine, for example, favorite topic of mine. Then we can see all these academic papers that we have here are now related to food and wine. Spices form the basis of food pairing in Indian cuisine, etc. Because this is GraphQL, we can show whatever part we want. So let's include also maybe the abstract and the year here. And then you get this data. So this is again something that separates Weaviate from these pure vector search libraries. You don't just get an ID back and then you have to retrieve a data object. You're doing this vector search, and what you get back is the whole object with all the parameters that you're interested in. So let me remove the abstract again so it's a bit easier to see, and let's go for a different topic. For example, let's go for machine learning. now you can see papers related to machine learning. And you can see that, as this is a very hot topic, most of these papers are pretty recent. So 2019, 2017. Let's say we're interested in the history of machine learning. So for this particular case, let's say I only want to show papers from 2016 or older. What I can do now is combine my fuzzy vector-based explore search with a structured scalar-based search, as you can do in a traditional search engine. So in the traditional search engine, you could only do the structured search, but we allow the combination of what you already know from a traditional search engine with the vector search. So let me add a where filter. And for this, I'm going to say the operator is less than or equal, and I want to operate on value 2015, or I want to say 2016, and then the operator is, the operator we have already, the path, so this is the field that I want to filter on, as you can see. So this is a structured search, so we can specify the individual property, and in this case, that would be the year. So let me run that again, and you can see now we have papers related to machine learning. They're still related to machine learning, but only from the year 2016 or older. And this works on any field. So this could also work on a string field. For example, let's say in the abstract, we need to contain a specific word. So let's say in the context of machine learning, it needs to have the word TensorFlow in there, for example. So let me type that in, TensorFlow, and run the search again. And as you can see, I'm seeing different results here. And if I want to check, you also include the abstract and run the search again. And then you can see that here, for example, the word TensorFlow is contained. And again, this is a combination of sort of this filter and ranking by a vector search. Now, all of these vectors that I'm doing here, like as you can see, I'm only ever specifying text. So this means I'm using Weaviate's semantic search extension where my interface is text. But if you have your own machine learning models, you could also just import your own vectors, and then in your search, you could just specify a search vector. So you have the option to use Weaviate sort of end-to-end just based on text, or you have the option to use your own machine learning models and use Weaviate as a pure vector search. As you were able to see on these example queries, it's quite fast, but how fast is it actually? For that, I have a simple benchmark here. So if we just run maybe one of those GraphQL ones, I've prepared that already. So here we're going for the concept of autonomous driving. And then we can see this result, the search with 10 results was returned in 28 milliseconds. That's of course not very representative because it's one query. All the caches that are involved for this particular query are now hot. So of course, that's not too representative. So for this, I've built a simple tool, a benchmarker that you can run on the explore function, you can specify a class name. In this case, that would be the paper class, the same one that we used in here in GraphQL. So here you can see it, the paper class. And then what this tool does, it picks 4 random words out of a dictionary and assembles a search query out of those 4 random words. So every search is going to be random. Let's say we just have one query and our parallelism is 1 for now. Then you can see here in this example query, it was just 1. It took 28 seconds, so mean and max is also, 28 milliseconds. So mean and max is also 28 milliseconds. So let's ramp that up to maybe, let's say, 100 queries. Then you can see we have a bit more variance. So 100 queries succeeded, that is good. And the fastest one was 10.4 milliseconds. So keep in mind, this is always on these 1.7 million papers that are in the data set. And this is not just returning IDs or something that you would get from a pure vector index, but this is also returning the data objects themselves. So in this case, the title. So in this query, we had the parallelism factored to 1. So essentially, what this means is this is just 100 sequential queries. So basically by the time the next query starts, there's no load on this Weaviate instance. This instance is running, this is a single machine. As said, we'll have a video about horizontal scalability later. Right now, this is just a single machine, and that machine has 8 CPUs. So let's maybe send 8 queries in parallel. And then what we can see is we still have very good numbers. The fastest query was 10 milliseconds. The slowest query was 39 milliseconds with a mean of 21 milliseconds. This is, by the way, always a 10 nearest neighbor search. So it's essentially the same query as you see here, 10 nearest neighbors for a random search term, or in this case for 100 random search terms. And since one search in Weaviate is always handled by a single CPU thread, if you go with the parallelism factor that this machine has CPUs and this machine has 8 CPUs, then you can see that we still have a good throughput here of 330 queries per second with a very low mean response time. So let's maybe ramp this up a bit. Let's go for 1,000 queries and try 16 in parallel. So this means on average now every CPU thread has to handle 2 queries at the same time. And you can notice that the mean time does go up a bit. We're at 37 milliseconds, which is still blazing fast for most use cases. Fastest is still around 10. Slowest now can go to 80, and we're at a nice 416 queries per second on this single machine. So let's maybe go for 10,000 just to increase the load a bit. And as you'll be able to see right now when this query finishes, we're still going to have a very nice response time, given that any single one of those is a unique search happening on 1.7 million papers. So I'm expecting this to take, yeah, there we go. Took 24 seconds. And again, the mean time, 39 milliseconds. The slowest query was 349 milliseconds, which is probably still acceptable in many use cases, but mean query time just 39 milliseconds, the fastest still 10. And we're still at around 400 queries per second on this single machine. So if you wanted more than 400 queries per second, you'd have to either use a larger machine or scale your Weaviate up horizontally. So that was my demo of Weaviate Standalone, of the current features that we have in Weaviate Standalone. And if you're interested in which features are available, we have this overview page in the docs, and you can see there's some green, but there's also some red. So everything that's red is something that is available in the current non-standalone Weaviate version, but not yet in standalone. But by December, when we release this as version 1.0, then all of these features will be in. So now that you've seen Weaviate Standalone in action, let's talk about the architecture behind it a bit. You've seen the example before where we created a class in our schema that we called paper. Now let's do the same thing again and see what happens underneath. So in our schema, we had, as we said, this paper class, which I'm just drawing right here. So we have one class, and that's called paper. This is the equivalent to, in a SQL database, you would have a table, and this would be called paper. In something like Elasticsearch, you would have an index. In yeah, you get it. So essentially, this contains all of our documents of the class paper. Internally, this paper class also creates what we call an index, and this index is made up of multiple shards, or can be made up of multiple shards. We'll get into the benefits and into the sharding strategies in a later video when we talk about how to set up a Weaviate for a distributed cluster. But for now, to keep it simple, because I just want to focus on how we index stuff, let's just pretend there's just one shard in every index. So this index with its one shard is essentially one self-contained unit. And in here, we have 3 parts. The first one is a key value store. I'll get into the details of what each of these mean in a second. The second one is an inverted index. And the third one is a vector index. So what happens if you import some documents? So let's import the first paper into this index. Essentially, we're now writing into these 3 parts. So the first one, the key value store, is very easy. That's something that's very essential in any kind of database. In this key value store, we simply store your document, your individual data object, by its ID. So if you go to the Weaviate API and you do something like a get on v1 things and then the ID of this particular paper, it just goes to that top index here and returns your paper directly. But that's essentially just a key value store. So what we also have, and the combination of those two, so let's maybe label them 1, 2, 3. The combination of 2 and 3, I think, is what makes Weaviate unique. So let's have an example query to show what these other do. Let's say the user searches for something that's close to autonomous driving. but also wants to limit the search to papers that were published between, let's say, 2011 and 2015. So let's pretend that this year is just an integer. It's like not a timestamp right now. Let's pretend it's an integer. So essentially what we're doing now is we need to find out which papers were published in between that time frame. And one way, a sort of brute force way, would be to just loop through all the papers and see when they were published, which means at even at this demo scale that we have here, which is something like, I think, 1.7 million objects, that would be a lot of searching for a single search query. So to help with that, we're using the inverted index. An inverted index is nothing new. You know them from, you probably know Lucene and Solr and Elasticsearch that's built on top of it. And there's plenty others. So an inverted index by itself is nothing new. Nevertheless, it's relevant in this architecture. So the inverted index is called an inverted index because essentially it doesn't index the individual objects, but instead it indexes the values that we have in the properties of these objects. So essentially in this inverted index for published, we now have 4 rows or 5 rows, 2011, 12, 2013, 2014, and 2015. And each of these rows contains a pointer back to one of the documents that we have stored in the key value store in one. So essentially, even if there are 1.7 million papers in total, this operation is relatively cheap because we essentially just scan 4 rows. And under the hood, this inverted index is running with BoltDB, which in turn uses a B+ tree. And a B+ tree is very efficient in these kind of range queries where you read data in order. So in our pretend example where the year is just an integer, we essentially just have to read those 5 rows, and each of those rows contains a pointer to a document. So this is essentially just an ID, this pointer. So up until here, if we draw the line here, you wouldn't need Weaviate for that. You could have done that with any kind of search engine out there. You could have done it with Elasticsearch, Solr, etc. So now is where the machine learning magic comes in. So assuming we're using the semantic search extension, that basically just means you always deal with text with Weaviate and all the vector stuff happens in the background. So assuming you're using that, this string autonomous driving in the beginning has been turned into a vector. So we know that the vector position of this word autonomous driving is a vector, something like 0 point, blah, 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 0 point, and so on. So essentially this very long number, usually in Weaviate, these are either 300 or 600 dimensions. And essentially, based on that number, we can now find other data objects that are very close to this query, or not other data object, but data objects. This is of course not a data object, this is just a search query. And to do that, we need our vector index. So essentially, after we're done with step 2, and we get the inverted index, we essentially now have an allow list, or if it's a very, very long allow list, we could also turn this into a deny list. And this allow list is something that we're passing into the vector index. The vector index itself, now I'll get into how that works in a second when we also talk about memory. But essentially the vector index is a pluggable thing. You can use whichever vector index you need for your purposes. The first one that Weaviate starts with, the first one that's on offer, is HNSW. And HNSW is one of the best performing vector indices out there. There's also Google Scan, which looks even more promising, but it doesn't have the kind of maturity that HNSW has because it's been out there for quite a while. So the first one is HNSW. Maybe in the future we'll have Google Scan. Something that our benchmarks have shown, though, is that in a real-life scenario, these sort of marginal benefits that an even better index provides are relatively slow, depending on what your use case is, because an index like HNSW is already very, very good. Okay, so now we're giving our allow list that we got out of 2 and our search vector that we got from before this persistence layer that happened in the application layer. We're giving that into our vector index, and then the vector index sort of just orders these IDs and cuts it off wherever the user set the limit. So essentially it says like the most relevant docs that you have for this particular search query are the docs number 17, 8501, 13, etc. So then the only step that we have to do is go back to the key value store and retrieve, because the user isn't interested in those raw IDs, but the user is interested in the actual objects. And the combination of those three is what makes Weaviate unique. So basically, if you compare Weaviate to a classical search engine, you would only have step 1 and 2. You wouldn't have step 3. If you compare Weaviate to one of the sort of vector search, I think they're usually called similarity search, libraries out there, like there's one from Facebook, there's the official HNSW implementation, there's plenty of those out there. They usually only focus on step 3. Step 3 is very important in this thing. But with Weaviate, we really want to deliver on this end-to-end thing. You start with a query here, and you get your final objects back, as you've seen in the demo before. Similarly, the ability to combine these sort of structured queries on scalar values, like published, between, and then you have these very sort of hard truths, like either it is published in that time frame or it's not. Combining that with this fuzzy vector-based search is also something that makes Weaviate unique. Not a lot of solutions out there offer this. And then even those that do, usually they store this data completely separately. So for example, you might see a solution where you have the vector search engine in like one completely separate thing, and then they say like, okay, you need to spin up a separate MySQL database or something. And well, maybe draw a database, like a database. Yeah, so this would be a very sort of separate solution, and then if you scale the database part even further, then, or if you scale the vector search part further, then how do you scale this? And essentially you'll always have queries in between. So what makes Weaviate unique here is that we say like, this is sort of a first class use case. We want to be able to serve a combined structured and vector search. So it was very important in our architecture that these two things, or these three things actually, are very close to each other. And I think that makes Weaviate absolutely unique. Okay, now before we get into the resource requirements of Weaviate, I very quickly want to talk about HNSW. HNSW has been out there for a while. It's not something that we invented. It's just something that we chose to use as the first vector index that's supported in Weaviate. But in order to explain the memory requirements in Weaviate, I very quickly want to go into the details here, because this is also something that sets Weaviate apart from other solutions. A lot of solutions are built around the idea that you can fit your entire data set in memory. And that means either you have a relatively small data set or you have a massive machine. And with Weaviate, we want to focus on those production use cases where cost also matters. So we said we don't want Weaviate to be, we don't want that requirement that everything always has to be in memory, because disks are of course much cheaper. But at the same time, we also don't want to give up performance. And I'll tell you how we achieve that, but let me very quickly talk about HNSW. So HNSW is a multi-layered graph, and the idea is that in these individual layers, let me draw the second one and maybe the third one, every object that you have in your database is contained in the lowest layer. So these are all your data objects, and they're all connected. Actually, they're not all connected, but they're very, very well connected. So the SW in HNSW stands for small world. The idea is it's a small world. You know someone who knows someone, and with 3 or 4 hops, you basically know anyone on Earth. So the idea with such a graph is that you have an entry point into this graph on a search. Then you inspect your individual neighbors. So let me maybe switch color here. Then you inspect your neighbors. And of course, your search query is also somewhere in that plane. So let's say the search query is here. And then you only proceed with a certain number of neighbors that are closest to your search query. So if this is your entry point, you would now say, okay, I found, let's mark it in green. I found this neighbor because it's the one that got me closest to the search query. And then you repeat the process. You pick the neighbors that are closest to the search query. So this one is a candidate, this one is a candidate, and then you see, okay, this one is the closest. And in our example, this is actually the best result because it's closest to the search query. If we only had that single layer down here, this would essentially be NSW without the H. HNSW makes this hierarchical. And the idea is that on each layer, you have fewer points than you did on the previous layer. So these match up, but on each layer you have sort of exponentially fewer data points. And this makes it quite efficient because essentially if the same query now comes in, we'd do the same thing again. So our query was somewhere around here. Let's say our entry point is here. Then we go back, and in this case, jump here. Then that's the closest on this layer. So we go down to another layer. On this layer, actually, we don't have any closer one. So we get down another layer, then we get here, and then we just have to make one more jump. So essentially, on the higher layers, these distances, they're much, much longer, and therefore you have to do fewer hops. And then on the lowest layer, you'll get all your data, but you need to have a high recall in your search, because of course, you still want to get all the results back. So this was a very, very brief overview of what HNSW is. If you care about it, read the paper. It's very interesting. There are also videos out there. So why am I telling you all of this? Well, of course, I want you to understand what's going on with Weaviate on the inside and how it can be so fast at these vector searches. But at the same time, I also want to talk about memory. So a lot of these implementations that you see out there for HNSW, they need to hold the entire model in memory, but at the same time, they also need to hold all of the vectors for each data point, which can be a lot of memory. In Weaviate, we have a slightly better approach. In Weaviate, we have a cache for some of those vectors, and the reason why it works so well with HNSW is essentially due to the layered approach. So we have a cache that's considerably smaller. So for example, on a data set with 1 million objects, it's absolutely enough to just hold 50,000 of them in memory, and it's still super blazingly fast. And the reason this works so well is because, well, you always start your search on the top layer. So you have very few here. So essentially the top layer is always going to be cached in memory. And then it goes down, and I don't know, you have maybe 10 layers in real life, and the top 5 or 6 of them would always be in cache. So even if you have to do a few disk reads for the lowest layer, it is still much, much, much faster than if you had to read everything from disk. In fact, it's not really noticeably different from having anything in memory, but we only need to reserve a very small amount of memory. So this is entirely configurable, of course. So if you say you need the absolute maximum performance out of your index, well, you can just make the cache as big as your entire data set is, if you can afford those machines, and if it's worth that extra bit of performance, then you can just do that. But for most use cases, you don't need that, and you don't need to spend the money. So essentially, the memory requirements for Weaviate are relatively small. So let's come up with an example of how many resources you would need to run Weaviate. So we said before, for a data set of 1 million objects, it's absolutely sufficient to have a cache of roughly 50,000 objects. So in my case, this of course varies, but this is just the default Weaviate case. In my case, one vector is 300 dimensions, and it's a float 32, so that's 1,200. So that would be around 60 megabytes for the vector cache. Obviously more is better, so let's maybe, because this is a very small amount, let's just go with 100,000 here. And then we'll end up at 120 megabytes, and that's still absolutely reasonable. Similarly, you need to keep the index itself, not the vector's position, but the index itself. So basically these links on these individual layers, they need to be kept in memory at all time. And I happen to know from my example before that on this 1 million data set, the index itself is around 600 megabytes. So that would be around 720 megabytes for the HNSW index itself. The application itself, of course, also needs a bit of memory. So let's roughly say that this ends up at 1,024 megabytes. So that would leave, what, 300 or so for the application. That seems reasonable. And then if you go back to these stores, these essentially act as memory mapped files. So they use the Linux page cache a lot. So anything that is frequently read can be kept in the page cache. So it's good to leave some space for the page cache. So depending on how much different data is being read, usually we would recommend that at least half the memory is reserved for the Linux page cache. So in that case, that would be, so this would be vector
Then we have page cache. Let's use the same amount again, which would make us end up at just 2 gigabytes for a 1 million use case. So let's say one of the example searches, a typical search that you do, is maybe just a I don't know, 10 nearest neighbor search, and that takes you 25 milliseconds. So this would translate to being able to do 40 searches per second. And a search like this is always single threaded. So essentially, if you just have one CPU, then you could do around 40 searches per second. That's assuming that these 25 milliseconds are actually full CPU usage, and that's roughly the case. That's enough for our calculation. So let's say that is plenty for your use case. Then you would have to pay for one CPU and 2 gigabytes of memory to be able to handle a use case of 1 million objects in production with very, very reasonable response times. Now, of course, if your load increases, you could scale it. This is too small, in my opinion, to start scaling horizontally, but you could. So it's still, at this point, it still makes sense to just increase the machine size to sort of a reasonable standard VM size. And at that point, you would then start scaling horizontally. But of course, if you have very varying demand, then you could also start scaling horizontally at that point yet. As said before, I'll create a later video at some point about how to use Weaviate in a distributed setting. For now, for the 1.0 release, we're just focusing on a single node use case, and then we'll have horizontal scalability later. And these numbers roughly go up linearly. So you can see that if you have a 10 million or 100 million use case, that it's still very, very reasonable numbers, and these would be very large data sets already. And this is all, as said, just for a single machine. And for the very large sort of billion and tens of billion use cases, then you could, of course, run Weaviate in a cluster horizontally scaled. The reason why I wanted to highlight this is because I think this is also something that sets us apart from our competitors, and especially from all these library solutions, because these all, or not all of them, but a lot of them seem to be focused on just sort of, you spin up something and you build your model and you run your queries and you shut it down. And for that, it doesn't really matter how much it costs. Like if you have a machine that needs 100 CPUs, and we know that use case very well because we use these kind of machines for training the underlying machine learning models that we use in Weaviate. If you have such a machine and you just run it for a day, that's not going to bankrupt you. But with Weaviate, we really want to target these production use cases. You have this running 24/7. You have this maybe running in a high availability setting, have for redundancy, for scaling, for higher throughput, etc. And there you pay these resources. So here it was very important for us to be able to serve a large use case on a very small machine. And of course, if you do need this absolute raw performance where you say like, okay, I don't want to have any kind of disk reads, I want to have every vector in there, well, you just increase the size of your vector index. But here we put it at 100,000, which would be generous 10% of the data set. As said before, 5% would probably also be enough. But you could also put that to 100%, and that would be 1.2 gigabyte in this case. And as you can see, that's still very reasonable. And maybe we would end up with 2 gigabytes for everything, and then if we want to have sort of the page cache accordingly, then we'd maybe be at a 4 gigabyte machine. So you'd have like one CPU and 4 gigabytes. That's still very, very cheap, and a lot of the use cases that we see do actually fit in roughly in that area. Like not everything is 100 billion objects, but if it is, we're happy to cater to them as well.
Thank you for watching this demo and this update. If you want to stay in contact with us, you can follow us on Twitter, you can give us a star on GitHub, you can sync up with us on our LinkedIn page, and of course you can sign up for our newsletter so you get all these updates, including when we publicly release version 1.0, including Weaviate Standalone. Thank you for watching, and see you soon.